Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled 555 Timer Monostable Operation. There exists within those bins of electronic components inside the lab an extremely versatile device which makes use of some of the basic sequential devices that we've thus far discussed. Don't exactly know where to put this within the lecture structure, so I'm putting it right here. This device is the 555 timer. There are numerous applications for this, and I'm only going over the two most basic ones. First one is monostable operation. Next one will be astable operation. And before we even discuss the 555 timer, let's discuss what a monostable device is. That is what's known as a one-shot. What does a one-shot do? It basically has a stable state, and it can assume the temporary opposite state for a temporary period of time, only which to revert back to its original state. So what a timing diagram for a monostable one-shot would look like is something like this. Okay, let's assume this is an active low trigger device, and what we've got is our trigger input right here, and at such and such a time it has an active low pulse. So what's happening is our output was a 0. So that is its stable state. That's monostable state. Once it's triggered, it can go to its opposite state for predetermined period of time, which I'm going to call TW, the pulse width, at which point it will revert back to its original state. And let's say another active low trigger occurs right there. What's going to happen? It's going to go ahead and assume that opposite state for that exact pulse width. Questions to ask yourself: what if these trigger pulses appear closer together and further apart? How would that affect the pulse width of some? Find that out in lab. But let's actually go to the application of the 555 timer used as a monostable device or a one-shot. All right, so let's discuss what 555 actually has on the inside. So you're going to grab it from those component bins. What you're going to see is kind of a tiny looking TTL chip. It's got 8 pins on it. They're from pin 1 to 8, ground, trigger, output. So those are obviously, that's our input and our output, trigger and output. A reset, control, threshold, discharge, and our supply voltage VCC. What's neat about this device, you don't necessarily have to have it at 5 volts. You can go up to 15 volts for a 555 timer, which is again one of those reasons why it's such an incredibly versatile device. Okay, internally, what does a 555 have in it? Most famously as a voltage divider with 3 5k ohm resistors. Do you get it? 555 timer. So we've got a supply voltage at the top of those, and then it's hooked to a ground. So there are 3 identical resistors, regardless of the resistor value. I know they're 5 kilo ohms, and regardless of the VCC, you should be able to figure out, I certainly hope you'd be capable of figuring out the voltage divider there. That is going to be 1/3 of VCC. That is going to be 2/3 of VCC. Don't believe me? Perhaps you've heard of Ohm's law. Perhaps you've heard of the voltage divider rule. Check your work. Make sure I'm not telling you something crazy. So the voltage divider rule, all it's doing, only purpose of that voltage divider is to give us these 2 reference points. 1/3 of VCC, 2/3 of VCC. And the next device that we're going to discuss is a voltage comparator. Okay, so this is totally different than a binary comparator, like a numerical comparator, which we've been thus far discussing. You've probably already even built a voltage comparator in your semiconductor devices and circuits class. All it's doing is comparing 2 voltages and giving you a logical output. Okay, so it's this interface between voltage on the left and logic on the right. It's comparing the plus input with the minus input. If the plus is higher than the minus, it's going to say true, because that makes sense. Plus should be higher than a minus. If the minus is higher than the plus, that doesn't make sense. The answer is false. So again, just the function of the voltage comparator. Let's say here, just say it's 3.3 volts on this one, and it's 4 volts on that one. Does that make sense? The minus is higher than the plus. The answer is false. Now let's say that that is 2 volts. Yes, the plus is higher than the minus. True. All it's doing is comparing voltages. What are the other components in the 555 timer? Well, an NPN transistor. I know you've just taken a course in semiconductor devices and circuits, and you've discussed all these fancy operational amplifiers and beta ratios. Don't worry about it, guys. Check it out. What's a transistor? It's a switch, and that's the only thing you need to know in this course. And honestly, for a lot of applications, that's all a transistor is. It's a switch. NPN transistor. This is the base. When the base for an PN transistor gets a logical high. It's almost like you could imagine, so here's our base, and it's getting a logical 1. It's almost like you could imagine a switch closing between our collector and our emitter. So it's closed. That's a closed switch. But if our base has a 0, what happens? The opposite. It's open. Okay, remember this for the NPN transistor. If the base gets a 1, it closes. If the base gets a 0, it's open. It's that easy. Don't you wish semiconductor devices and circuits was that easy? Okay, the next device inside a 555 timer is an SR latch. I certainly hope you're familiar with this guy. Let's just do a super basic review about what an SR latch does. When I am, and it's like active high, so I'm neither setting nor resetting this device. What does Q do? Well, Q stays the same. Now I set this thing. What happens to Q? It sets to 1. Now I go ahead and reset that device. What happens? Q goes down to 0. In this particular case, we're not going to do this. We're never going to go ahead and simultaneously set and reset, so we can kind of ignore that. But again, just understand how an SR latch works before we begin, because we're going to throw a twist in it. Quite literally, we're just going to flip it upside down. The reason why I flip it upside down is because it's easier to draw the drawing that way. And just do a review. How does an SR latch work when it's upside down? Well, exact same way it's when it's upright. When I'm neither setting or resetting it, what does Q do? And what I'm talking about is this Q right there. What's that Q? Because look at this string of inverters. And I know it's kind of a pain, but I'm trying to stick with a traditional diagram for the 555. What happens to that Q? Well, it's inverted, so that's not Q, and then re-inverted again, so that's Q. I know, it's kind of a pain, but we have to kind of use that not Q signal. All right, so neither setting nor resetting, what happens? Q stays what it was before. Not Q stays what it was before, and our final Q stays what it was before. What happens here when I set this thing? When I set it, Q goes to 1, not Q goes to 0, and Q is 1. All right, now I go ahead and go back. I'm staying. If that Q was a 1, it's going to stay a 1. Now I'm going to go ahead and reset it. What happens here? Q goes to 0, not Q goes to 1, Q goes to 0, and then I can go back to a stable state or a stay state. What's going to happen to Q? It's not going to change. It's at 0, not Q's a 1, Q's a 0. How does the SR latch behave when it's upside down? The exact same way. All right, let's take all these components that we've just discussed here. We're going to take our voltage divider. We're going to take 2 voltage comparators. We're going to take that single NPN transistor, and we're going to take our SR latch modified. What are we going to do? We're going to hook up 2 comparators to the voltage divider rule. Okay, so look what's going on here. The threshold is the input for the top comparators plus. Okay, remember back to our input diagram, or excuse me, our pinout diagram for the 555. The upper comparators minus input, it's on that 2/3 of VCC input. Where's its output going? We'll figure out where it's going later. Okay, the red, i.e. the lower comparator, it's plus input. It's on that 1/3 VCC, and I've got a trigger going to the outside of that chip. Where's its output going? We'll figure that out in a second. Some diagrams leave that voltage divider in there, and it's really confusing that way. So what we're going to try to do is just do this, because check it out. What's our VCC in a 5-volt system? Well, it's 5 volts. Okay, so regardless of what those resistors are, I know they're 5Ks. What's going to happen is the blue, i.e. the upper comparator minus input, is always going to have 3.3 volts on it, and the red lower comparators plus inputs is always going to have a 1.6 volt input on it. So what is the blue comparator comparing? It's comparing threshold with 3.3. When threshold is higher than 3.3, it's true. When threshold is lower than 3.3, it's false. What's the red lower comparator doing? It's comparing trigger with 1.6 volts. When trigger is 0, the output is true. When trigger is higher than 1.6, the output is false. So now what are we going to do? We're going to take those outputs of those comparators and put them into our modified SR latch. So when both comparators are giving a 0, what is our mode that device is in? Well, it's in a stay mode, whatever it was before. When the trigger is lower than the 1.6 volts there, it's getting a set command, okay, and the device is going to set. When the threshold is higher than 3.3 volts, it's going to get a reset command, and we're going to try to never simultaneously set and reset that. Let's add another device. Notice we took that intermediary value of not Q now. Now we're feeding that to the base of that NPN transistor and that is going to the discharge external to this device. Okay, so check this out. When is that thing open and when is that thing closed? Well, it's an NPN transistor. So when the base has a positive, i.e. a 1, it's going to close. Okay, so when not Q is a 1, it will be closed. Got it? What's the Q value when it's closed? Well, the opposite of not Q, 0. When is it open? Well, when that base is getting a 0. So not Q has to be a 0. When it's the Q, what's the Q value when it's open? Well, Q is the opposite of not Q, so it's going to be a 1. Just helps to, I know there's double inverters there. It's kind of confusing. It just kind of helps to walk through this. That's the basics of a 555 timer, and nothing is going to change between this description and our next description when we actually use the 555 timer as an astable device, i.e. an oscillator. This application is a monostable, i.e. a one-shot. The only thing we're going to do is we are going to go ahead and add some external components in a certain configuration to produce a monostable device, one-shot device. This description that I've done thus far, before you watch the astable operation lecture, go ahead and refamiliarize yourself with the contents of the 555. So let's actually go into monostable operation. For monostable operation, we're going to go ahead and take an external resistor R1 and an external capacitor C1, and we're going to go ahead and see how the output behaves with reference to an active low trigger. And I'm going to give you guys the punchline right up front. Basically, the output is going to go high at the same time that that active low trigger goes low, and the output will stay high for a pulse width of TW 1.1 times R1 C1. You should be able to remember that. And we're going to go ahead and see how this thing works. At which point after that TW, basically it's going to revert back to its original monostable state, in this case a 0. So monostable operation, like I said, we add an external R1 and it goes from VCC to threshold. We're going to tie, so I'm talking about this guy here. We're going to tie threshold to discharge, and we're going to take an external capacitor, discharge to a ground. And again, our trigger, what's it looking for? Well, it's constantly at a high and it's looking for a low. What we're going to do is basically go into our steady state. Okay, what is steady state? Steady state, the trigger is high. It's not being triggered. And our Q output is 0. Okay, so pretend it's 0. What's our transistor state? If Q is 0, what is the base of that transistor receiving? It's receiving a 1. What does a 1 do for an NPN transistor? It closes. It's closing that switch. What happens now when that switch is closed? Well, basically, current flow is going to go through that resistor, and it's going to get to this capacitor. Well, why would it go to the capacitor if it's got a closed switch? Basically, it's shorting that thing to ground. No current is flowing into that capacitor to go ahead and charge it up. What is the inputs to each one of those comparators? Well, when the current path is as such, basically all voltage is lost across resistor R1. So the threshold input, the positive input, is going to have 0 volts. So what does the output of the blue comparator? Well, the plus is at a 0, the minus is at 3.3. That doesn't make sense. So that's a 0, logical 0. Our trigger input, it was a 5. It's a constant logical high right now. And the plus input for that red comparator is 1.6. Does that make sense? The minus is higher than the lower. The plus answer is no. So 0, 0. What's happening there? Well, it's neither setting nor resetting, so that mode is stay. Hence the name steady state. It's going to stay in the state all day until our trigger goes low. Okay, so let's go ahead and see what happens here. So trigger goes low, and we've got a little mini timing diagram right here. So trigger goes low, what happens now? So I've got 0 volts right there. The capacitor is uncharged because up to this point there's been a short circuit, and in addition to that short circuit, if there was any charge in that capacitor, what's happening? Well, it's being discharged to ground, hence the name discharge, okay, for that pin. So what's going to happen here? The comparator input for the lower comparator has changed. Okay, what happens there? There's a 1 there. The capacitor is initially uncharged. What is our threshold? It's initially uncharged. It's going to be 0 volts. So what's happening here is that is still a 0, so it's not resetting, but it is setting it. Okay, see what's happened here? We are setting it, not resetting it. The mode is obviously set. What happens? Well, Q goes to a 1, not Q goes to a 0, and our output Q becomes a 1. So what happens in our timing diagram? Q becomes a 1 at that moment of transition for the trigger. The trigger goes low. So our Q output is now 1. What happens to the transistor? Okay, if not Q is a 0, that transistor turns off, and there is no longer this discharge path. Basically, all current is now has to flow into this capacitor. And what does that capacitor do? It charges up, starting to charge right here. Let's take a brief moment to review what is the voltage across a capacitor when you've got a resistor and capacitor in series. So this is our capacitor charging review. Hopefully this is a review for you. What I've got here is the general formula for this. There is an initial voltage. Let's assume there's an initial voltage, and if we left the capacitor for long enough, there should be a final voltage which it will charge up to. At such and such moment, T0, this capacitor with an initial voltage is allowed to have current flow into it, i.e. it's charging up. What's going to happen? It will eventually charge up to the final voltage after 5 time constants from T0, whatever that initial time was. So how does this thing behave? What's the mathematical relationship for this curve here? Well, the answer is right here. The voltage across the capacitor is equal to the final voltage plus parentheses initial voltage minus final voltage parentheses times this magic number E raised to the negative T over tau. What's tau? What's R times C? That's the general formula, which you can use for all purposes. For our particular purposes, well, it's 5-volt system. So what's our final voltage? Our final voltage, if we left this thing totally alone, which we won't, it should eventually charge up to 5 volts. What's our initial voltage? Well, it was initially discharged, 0 volts. What's our tau? RC. Go ahead and stick it in the formula. What do you get? Take your VF is VCC. What's your initial voltage? 0 volts. Let me go ahead and use a highlighter for that. What's our final voltage VCC? What's our initial voltage? 0 volts. You do some math and magic, what you get is this VCC times parentheses 1 minus E raised to the negative T divided by tau parentheses. And that graph looks like this. That thing is going to charge up from 0 volts to 2/3 of VCC, and we'll see in a second why. But if we left it alone over 5 time constants, it should charge up to 5 volts. And this is pretty critical right here. At what time? So I know I've given you the formula. I took our general formula right here, applied it to our specific circumstances, and we came up with this formula right there, which is, yeah, that's nice. But what I want to know is this question, and you'll see why 2/3 is pretty important. How long does it take from T0 to charge up to 2/3 VCC? Well, let's answer it. Just put in those numbers. Well, what is VC of T? Well, now it's known. I know I want it to charge up to 2/3 of VCC. I take that initial formula right there, and all I'm solving for is that time right there. So what I do is the first step, I basically go to divide VCC. I'm going to go ahead and get rid of my 1, get rid of that negative sign, take the logos naturalis of both sides. What's the logos naturalis of 1/3? It's negative 1.1. And what the logos naturalis does, it gets rid of E, so you get negative T over tau. Get rid of the negative sign because it's on both sides. Now all I'm going to do is solve for little t, and what is my tau? It's 1.1 RC. Oh my gosh, that's the exact same formula that I had for the pulse width. So basically, it will take a number of seconds equal to 1.1 RC for the voltage across that capacitor to charge up to 3.3 volts. Or 2/3 VCC. The point of this is why is that 2/3 VCC important? Well, here, check it out. Because at this point here, the threshold, it's looking for 3.3 volts. That's why that is such a critical time to worry about here. Before we get to the point where it's hitting 3.3 volts, I want to go ahead and talk about this trick. Okay, so I know I just did some math and magic, and we are looking for that 3.3 volts on threshold, but realize this right here, the trigger. Okay, the trigger was active high. It wasn't active low. It basically was brought low briefly, and it came back up. And the point about this thing is here, you'll see here in a second what we're going to do when we go through this. The point is that active low pulse trigger should probably be substantially smaller than our Q output. Because if you don't, you're going to have some problems, because if you kept the trigger low, it wouldn't work out very well. So let's go ahead and just do this quick analysis right here. Let's say VCC is not, voltage across the capacitor, VC, is not yet reached 3.3 volts. So that threshold, the upper comparator, is not going to change states just yet. I just want to look at the lower comparator. Let's say, I don't know, just say it's 2 volts. Okay, so the capacitor is charging, as shown in this gray graph up here. Okay, capacitor is charging. It's at 2 volts. Okay, what's the voltage input right now for this threshold? 2 volts. The blue comparator, what's happening there? It's still a 0. What happened though to our lower comparator? If trigger went to 1 or 5 volts, okay, what happens there? It's 0. We were initially in a Q1 state from our previous transition. When we got that lower trigger, we were in a Q1 state. Well, what we're going to do is we're going to stay in that Q1 state for a certain amount of time. Again, that is not Q is 0, Q is 1. When it's not Q, we are still staying in that charge up state. Okay, so it's a little intermediary state right there where the trigger has disappeared. The active low trigger has disappeared. Now, what happens? Capacitor voltage is charging up and up and up, and eventually it's going to reach that 3.3 volts. At what time? Well, probably at 1.1 RC. And here's what happens, okay? Because again, this is 5 volts here. Once that threshold reaches 3.3 volts and perhaps goes a little bit higher, what's going to happen here is the output for that upper comparator is going to go ahead and change to a 1. The lower comparator is still at a 0. What happens? We reset. Q goes to 0, not Q goes to 1. What happens there? That transistor turns back on. Whatever voltage, whatever electrons sitting on that plate of that capacitor instantly discharged. And again, Q here has gone to 0. So what we're showing here on this graph is VCC, it got to 3.3 volts. That discharge transistor turns on, instantly dumps its voltage. Q goes back down to 0. And now what we're going to do is we're going to basically return to our steady state. Our capacitor fully discharges. What happens? Our threshold input, it's now 0 volts. What happens here? This is going to be a 0. This was a 0. So we're back to that stay state. So we were a 0, we're going to stay a 0, and we've basically returned to our steady state. So it may take a couple times to go ahead and review the steps and procedures through there of how all these components interact. But notice what I've done here is kind of giving you this cheat sheet. Through every single one of those stages, you should be able to answer the following questions. The transistor state, is it closed or open? Where's the current path? What's my threshold input? What's the output for that comparator? What's my trigger input? What's the output for that comparator? What's my set command? What's my reset command? Given those sets and resets, what's my mode? And how does Q behave given that? Externally, how might this thing work? Well, the 555 is going to look like this, obviously, with its 8-pin inputs and outputs. And what I want to do, I'm going to tie my ground to ground, obviously. I'm going to tie my reset to +5. I have not discussed the reset. What the reset command is within that pulse width. Let's say you've triggered it, and if you want that to be reset during that pulse width, you have to give that an active low. You can see some from the full diagrams how that reset is hooked up there. Basically what it's doing is resetting that modified SR latch. And then what I'm going to do is I'm going to take my, obviously, VCC to my pin 8. I'm tying my discharge and threshold together. I'm taking a resistor from +5 to the threshold and discharge. And then from there, I'm also taking that capacitor to ground. What's this control input, which I have not discussed? Well, the control input goes to the bottom of the first resistor in that voltage divider rule, so I could potentially bias it beyond up or down from 2 or 2/3 volts. Again, one of those incredibly versatile devices. I've given you components, R1 and C1. I've got a 1K and a 0.047 microfarad capacitor. What is the pulse width of this configuration? Well, it's right here, 1.1 RC1. So when trigger goes low, the output should go high for 1K times 0.047 times 1.1 should be 51.7 microseconds. One of the questions that you might ask yourself is, what's the fastest I can trigger this at? If I made the trigger input slower, how would this behave? Let's say if I was triggering at 10 kilohertz versus 20 kilohertz. Basically that trigger input, the active low, is coming along once every 10 kilohertz or 20 kilohertz. How would that pulse width behave? Well, the answer is it won't change, okay? Because that pulse width is configured by these external components, not the trigger input. The question remains sometimes is, okay, I want to have a 50 millisecond pulse. How do I do that? Well, in the data sheet of the 555, there's graphs like this, and I'm actually kind of doing this by memory. I don't know if it's T's on the left or C's on the left or T's on the bottom or C's on the bottom. Let's just say for this example right here, it's T is on the left, the vertical axis, C is on the right and the bottom axis. What you've given is these graphs, these lines for certain resistors. And let's say you want a pulse width of that time period. If you're using a 1K resistor, just walk along till you hit the 1K and go down and read what the capacitance value is. If you're using a 10K, keep walking till you hit the 10K, go down and read the capacitance values. These are very general graphs, and if you want something very specific, you're going to have to zoom in, zoom in, zoom in. And again, are you going to have a 0.0413 capacitor? No, you're not. You're going to have standard capacitor values. So you've got to get it as close as you possibly can using those components. The other thing about these resistors too, just think if you need a custom resistor, just use a potentiometer to perfectly dial that into the exact pulse width. Okay, this concludes the lecture about the 555 timer monostable operation. We'll go ahead and discuss in the next lecture using the basic core of this first introduction to use this in an astable operation, i.e. an oscillator, or basically making a clock.